In this video, we're going to begin our discussion of anti-differentiation. So at this point, we know a lot about differentiation. We have a lot of strategies to calculate derivatives, and we also know of a variety of different applications for differentiation, including finding maximum and minimum values. So we're going to start our discussion of anti-differentiation, which also requires a variety of different techniques and also has a variety of different applications. So first off, what is anti-differentiation? Well, based on what you know about the prefix anti, you may be able to guess what anti-differentiation is. Anti-differentiation is what we can think of most generally as the process of reverse differentiation. So essentially, if we were to take a function and differentiate it, we find a derivative. If we were to reverse that process, then we perform the process that we're going to refer to as anti-differentiation. So essentially, anti-differentiation asks and ultimately answers the following question. Given a particular function, what other function has this as its derivative? So think of it as starting with a function that represents a derivative, something that resulted from differentiation. When we take an antiderivative, we're asking what function did we have to start with to end up with this particular derivative? What would the function be to result in this particular derivative? The function we find to answer that question is what we call the function's antiderivative. And I know these are long words to write. These are definitely $5 words. Anti-differentiation, antiderivative. Now, the process we use to find an antiderivative can generally be called anti-differentiation. Sometimes we'll call it integration. And integration tends to be the term we use more frequently. You'll find that I'll use these terms potentially interchangeably. Typically, I'll use integration. It's easier to say, right? So integration, anti-differentiation are considered essentially the same process. So here's a more specific representation of how a derivative and how an antiderivative are related. So we're familiar with this kind of notation. So we're taking the derivative with respect to x of some function of x, what we're calling capital F, of x, and potentially a constant added on. And when we take the derivative with respect to x of this function and this additional constant, we end up with another function f of x, in this case a lowercase f. Now keep in mind, when we have a constant like this added on, what happens when we differentiate a constant? Well, we know that goes to 0. So once we differentiate our function f, we end up with its derivative, what we're calling lowercase f, and differentiating a constant takes it to 0, which means the constant disappears. This is how we're going to express an antiderivative. So if this is our symbol, what we can think of as the symbol to indicate that we're taking a derivative, there's also a symbol to indicate that we are integrating or taking an antiderivative. So this is going to be the symbol for integration or anti-differentiation. It looks like a large S. And then next to that, we're going to write the function that we are finding the antiderivative for. So essentially, if we differentiated a function to find its derivative, we are integrating or anti-differentiating the derivative in order to end up with the function we started with. So this is the notation. We notice we have two parts to this notation. So we have what we call the integral symbol plus this, which we'll talk about in just a minute. This is the expression telling us to take the antiderivative of this particular function. And when we take the antiderivative of this function, again, we're asking the question, if this is a derivative, what function did we have to start with in order to get this derivative? Well, we know based on this statement that this was the function we started with to get this derivative. So the antiderivative of this particular function takes us back to the original function. So f of x plus c. Now notice the c comes back. This constant that we're going to call c is called the constant of integration. And we're going to see this present in pretty much every single antiderivative we find. So recall, we just talked about this a moment ago, that differentiating a constant results in 0. In other words, the constant disappears. So we have to take into account that when we reverse the process, in other words, we anti-differentiate, we integrate, the unknown constant potentially reappears. So again, just to clarify that, we start with a function of x plus potentially an additional constant. If we differentiate, that constant goes to 0. We know there's a rule for that. When we integrate, when we take the antiderivative, we have to take into account that we're treating this as a derivative, and so we're reversing the process of differentiation. When we reverse the process, it's possible that a constant reappears. Essentially, this constant that we have right here that potentially differentiated to 0 could potentially reappear when we integrate. So all we really have to remember there is every time you take an antiderivative, you're going to have that additional constant added on, and typically we just use the label C. Now, some official terminology. The expression on the left-hand side is what we call an indefinite integral. Think of that as the name of the problem you're solving. So you see something like this. This is the problem you're solving. This is called an indefinite integral. You're evaluating an indefinite integral. And we've seen this symbol dx before. We called this a differential. And I mentioned when we talked about differentials that we would come back to these. This is when we're going to come back to this. So the symbol dx, we know in general that means a small change in x. That essentially is telling us that x is the variable of integration. So there are certain problems where we may have more than one variable involved. The same kind of thing can happen with a derivative. The dx is telling us most specifically that x is the variable that we're integrating with respect to. There's also a little bit more to this than just specifying our variable, but we'll talk about what that means a little bit later. So just as the notation dx tells us to take the derivative with respect to x, the notation integral symbol dx, where we sub in our function in between those, tells us to take the antiderivative with respect to x. In other words, to reverse the process of differentiation. Think of the function given as a derivative, reverse it to find the individual original function that would have resulted in that derivative. So some antiderivatives we can calculate just based on our knowledge of derivatives. Essentially, we're just reversing the process of differentiation. If we're really comfortable with differentiation, then typically we can figure out how to reverse that process. So let's try a few examples. We want to use what we know about derivatives, about our derivative rules, to determine each of the following indefinite integrals. So we want to take the indefinite integral of 8 with respect to x, or in other words, find the antiderivative of the function 8, just a constant function, with respect to the variable x. So remember, we're reversing differentiation. We're asking the question, what function would we start with that would result in this as its derivative? So in other words, if we took the derivative with respect to x of this function, the result would be 8. We're trying to answer the question, what would that function have to be to give us 8 as its derivative? Well, we know if we were to use the power rule that we start with powers of x and then we differentiate down and eventually we can end up with a constant. We end up with a constant whenever we differentiated something that was linear. In other words, something where there was a power of 1. So if we were to start with the function 8x, where x has an exponent of 1, then taking the derivative of 8x would give us a value of 8. That would be the derivative of 8x. So the antiderivative of 8 is 8x. That's going to be the function that reverses the process of differentiation. But we also have to remember that it's possible we had an additional constant added on. So essentially you can check your work by thinking of differentiating this particular function. What would happen if we differentiated this function? Well, differentiating this term would give us the 8, which is what we were anti-differentiating right here. And differentiating the constant, well, we know the constant goes to 0, and so we don't see it right here. So we include that plus c to indicate that potentially there's a constant added on in order to take us back to this value as the derivative. So this function is going to be our antiderivative. Now let's try another one. We want to take the antiderivative, or the integral of 3x squared with respect to x. So again, what is this asking? It's saying the derivative with respect to x of some function was 3x squared. And again, we're asking the question, what is that function that we differentiate to get a derivative of 3x squared? Well, again, this is a situation where we probably applied the power rule. Remember, the power rule says you start with an exponent, you bring it down, it becomes a factor that's multiplied, and then you decrease the exponent by 1. So what function would we have to apply that process to in order to get a derivative of 3x squared? Well, if we started with an exponent of 3, that would bring down and provide an exponent of 3 right here, or excuse me, a factor of 3, and then we would decrease our exponent by 1. So that means our antiderivative is going to be x cubed. X cubed would be the function that we would differentiate that would result in a derivative of 3x squared. And again, we're going to add on that unknown constant to indicate that if we differentiated this whole function, we'd get the function of x from x cubed, but we could also potentially have an additional constant added on. We differentiate that, that goes to 0, and so this would be the value we'd end up with in either case. Okay, let's try a couple of our special cases that we've looked at recently. So the antiderivative of e to the x dx. In other words, the derivative with respect to x of some function is e to the x. What is that function? Well, this was one of those special cases we looked at. E to the x was a specific special function that we looked at because it has a very special derivative. If you were to differentiate e to the x, the derivative is e to the x. So if you were to anti-differentiate e to the x, it takes you back to a function of e to the x. So e to the x is its own derivative. It's also its own antiderivative. So the process is going to work both ways. And again, plus c, because there could be an unknown constant that differentiates to 0 when we apply this process. And then very last one, if we take the derivative with respect to x of some function, the result is 1 over x. Now this was also one of those special cases. 1 over x is the same thing as x to the negative 1 power, but we recognize that that particular output could not result from use of the power rule, because if we end up with an exponent of negative 1 in our derivative, that means we would have had to start with an exponent of 0 to use the power rule, but an exponent of 0 means the variable's not even there. So having this as a derivative relates to a special function, a special case. The function that resulted in 1 over x as the derivative was the natural log function. So the antiderivative of 1 over x, taking us back to the function that we differentiated, would be the natural log function. And I'm going to write the natural log of the absolute value of x, and I'll explain why in just a moment, plus c, plus our constant of integration. So why the absolute value? Well, take into account here, this function 1 over x, what we were anti-differentiating, what we were integrating. X can be anything we want in this case, and it would be perfectly fine, except for 0. We can't have a 0 there. But x could be a positive or a negative value, and this would be defined. For the natural log function, that is not so. So natural log, any logarithm, is actually only defined for positive inputs, inputs that are strictly greater than 0. So we have to indicate that for anything plugged into this function, the absolute value bars will take it and make it positive. So if the value of x were already positive, the bars don't change anything. If the value of x were negative, they would flip the sign and they would make it positive so that this expression is defined. So if x were already greater than 0, then we could just think of this as plain old natural log of x plus c. But in general, when we antidifferentiate and we end up with a natural logarithm, we're going to provide those absolute value bars to take care of that potential issue. So again, as long as you're fairly comfortable with differentiation, in a lot of cases you can just identify the antiderivative by reversing what you know about the derivative rules, essentially working backwards. But for cases where it's maybe a little bit more complicated, you can't just look at it and reverse differentiation, we're going to provide a series of antiderivative rules. Just like we have derivative rules, we have antiderivative rules. And in a lot of cases, they're going to look very familiar. They'll look very similar to the derivative rules, but essentially they'll result in us applying our derivative rules backwards. So we have a constant differentiation rule. We have also a constant anti-differentiation rule. So the constant rule says that if we're anti-differentiating a constant, k is a constant, with respect to our variable x, then the result is going to be k times x plus our constant of integration. And we can always check our antiderivative by differentiating again. So if we differentiated an expression like this with respect to x, thinking of x as the actual variable, well, we bring down the exponent, it becomes a 1, so 1 times k, and then the exponent decreases to 0, which means the x goes away, and so we would just have the k that we started with. So this will be the antiderivative of any function of this form. Now, more generally, we also have a power rule. So we have a power rule for differentiation. We have a power rule for anti-differentiation. It's going to reverse what we do when we use the power rule to take a derivative. So let's review what happens when we use the power rule to take a derivative. So if we're taking the derivative with respect to x of some function that has an exponent, remember, what we do first is we bring down the exponent, it becomes a coefficient, and then we decrease the exponent by 1. And the order we do that in matters. So the first thing we do is multiply by the current exponent, and then the second thing we do is decrease the exponent by 1. So that essentially summarizes the power rule for differentiation. Now the power rule for anti-differentiation reverses that. So not only do we do things in the opposite order, but we also reverse the actual operations. So multiplication reverses to become division, and decreasing the exponent reverses to become an increase of the exponent. So we do the opposite operations, but we also do them in the opposite order. So the first thing we're going to do to anti-differentiate something where the power rule would apply is to not decrease the exponent, but increase the exponent by 1. So when we anti-differentiate, we're going to take what we started with and increase our exponent by 1. So we go from n to n plus 1. And then rather than multiplying by our exponent, we're going to divide by the new exponent. So an easy way to write that is going to be multiplication by 1 over that exponent. Plus c, always plus c. And so this is going to be the expression for our antiderivative. We're not going to multiply by the exponent and then decrease it. We're going to increase the exponent and then divide by that new exponent. So opposite operations, opposite order. The idea here is that we are inverting the process of differentiation to perform the process of anti-differentiation. So this is going to encompass a lot of situations, just like using the power rule for differentiation does. And then let's just summarize what we noticed about logarithms, about exponentials based on those examples we just worked. So if we take the antiderivative of 1 over x, again, we're asking the question, if this is the derivative, what function did we differentiate to get that derivative? And so the function we differentiate would be the natural log of the absolute value of x plus our constant of integration. Or we can just say natural log of x, no bars, plus c, if we know that x is greater than 0. If we don't have any information about x, then we assume we're going to have to put the absolute value bars. And then last but not least, our exponential rule. If this is our derivative, if e to the x is our derivative, what function resulted in that derivative? Well, e to the x resulted in that derivative. We differentiate e to the x, we get the same function e to the x. We anti-differentiate e to the x, we also get e to the x. So e to the x plus c. So let's do a few examples just practicing using these rules, the constant rule, the power rule, and then the logarithm and exponential rule. Okay, so we want to find the following indefinite integrals, and don't forget that plus c. Just get in the habit now of putting that plus c, and that'll take care of itself. So we want to anti-differentiate the function x to the 7th dx. In other words, we're asking the question, if this is our derivative, what function did we differentiate to get that derivative? So in this case, we're going to use the power rule. So let's review that. The power rule says take the current exponent and increase it by 1, and then divide by that new exponent, or you can think of that as multiplying by 1 over that exponent. So we're going to increase our exponent by 1, which takes us from a power of 7 to a power of 8, and then we're going to divide by that new exponent of 8, or alternatively multiply by 1 over 8, plus c. How can we check this? Well, if we differentiate this function, we should get back to what we started with. So imagine differentiating this particular expression. That would require the power rule for differentiation. So we'd bring down our exponent. That becomes 8 times 1 over 8, which is just 1. And then decrease the exponent by 1, which would give us x to the 7th. And of course, the constant differentiates to 0. So that means that our antiderivative checks out. Now this is also going to apply if we have an exponent containing a fraction or a decimal. So in this case, our exponent is 2.5. The same procedure applies. So increase the exponent by 1. Well, if we're starting with 2.5 and increasing it by 1, that's going to become 3.5. And then we divide by that new exponent, or multiply by 1 over that exponent, plus c. Now the fraction out front is maybe a little bit troubling. The fact that we have an exponent that's decimal here and one that's decimal here isn't as problematic. Typically the rule is if you start with decimals, you can report decimals at the end. But suppose we maybe want to write this in notation we're a little bit more familiar with. So 1 divided by 3.5, I'm going to put that into my calculator. So 1 divided by 3.5, and I get an awful decimal, but remember you can convert to a fraction using the math menu and the arrow frac operation. And that converts to 2 over 7. So my coefficient could be rewritten as 2 over 7. Now what about that exponent of 3.5? If we don't want an exponent that has a decimal, well, we can do the same thing. So I'm going to type in my decimal, and then I'm going to convert it to a fraction. And that converts to the fraction 7/2 plus c. And again, I can check my antiderivative by differentiating. So with the power rule, we would bring down the exponent, multiply. So what would that look like? We'd have 7/2 times 2 over 7. Well, 7/2 times 2 over 7, picture the 2's and the 7's both canceling out, it would leave us with a 1. So we have a coefficient of 1 here. And then we would decrease our exponent by 1. Well, 7/2 minus 2 over 2, which is how we think of 1, would be 5 halves, which is equivalent to 2.5. So that checks out, that verifies our antiderivative. Now what about the next example? Well, we're familiar with what to do with square roots at this point. What we do with them for differentiation, we also do with them for integration. So I'm going to start by rewriting this in the form that we typically rewrite it in, which is in fractional exponential form. And that's going to be the function I'm going to anti-differentiate. So increase the exponent by 1. What would that look like? Well, if we increase 1/2 by 1, we're adding on 2 over 2, which would take 1/2 to 3 over 2. And then we're going to divide by that new exponent, or multiply by 1 over that exponent, plus c. Now we definitely don't want to leave the coefficient like this, so if it helps, put it in the calculator. 1 divided by the fraction 3 over 2, and convert that back to a fraction, and we get 2/3. Now technically we can avoid using the calculator for an operation like that if we just recognize what this expression is saying. 1 over anything is another way of saying take the reciprocal of that value. 1 over something represents the reciprocal. So if the number we're taking the reciprocal of is 3 halves, well, the reciprocal of 3 halves is going to be 2/3. So that's where that 2/3 is going to come from. And again, we could check this by differentiating. Imagine bringing down your 3 halves. Well, we'd have 3 halves times 2/3, which goes to 1, hence the coefficient of 1. And then we would decrease our exponent by 1, which takes us from a 3 halves to a 1/2. So that does check out. Okay, last one, the antiderivative of 1 over x cubed dx. And again, just like with a square root, we also have a special technique we use to rewrite something like this when we want to take the derivative, or here when we want to take the antiderivative. So we know anything with an exponent in a denominator could also be written with a negative exponent. So 1 over x cubed would be the same thing as x to the negative 3 power. So we're anti-differentiating x to the negative 3 power. Now, just as it didn't matter that we had a fractional exponent, it doesn't matter that we have a negative exponent, as long as the exponent is not negative 1. What's the issue with an exponent of negative 1? Well, if you increase the exponent by 1, negative 1 goes to 0, which means your variable disappears. The case where we'd have an exponent of negative 1 is actually this case right here, and we anti-differentiate and we get a logarithm, not a new exponential expression. So here that doesn't apply because we have an exponent of negative 3. So based on the power rule, we're going to increase the exponent by 1. Now be careful here, we're starting with a negative value. So as we increase it, it just becomes less negative. So increasing would take us to an exponent of negative 2. And then we're going to divide by that new exponent plus c. Now, in general, we don't leave negative exponents for the answer. We convert it back to something not involving a negative exponent. But we know the negative exponent says just take it to the denominator, take its reciprocal. Now the negative here, we can just bring out front, so that's going to be negative 1/2. And then we're going to have an x squared in the denominator, plus our constant of integration. So just like the power rule for differentiating is pretty versatile, the power rule for anti-differentiating is also pretty versatile. Now let's add on a couple of additional rules. They're going to help us generalize our antiderivatives a little bit better, look at some slightly more complicated situations. So other rules, these are also similar to rules we have for differentiation. So constant, specifically when we have a constant multiple of a function. We have a function multiplied by a constant. So a constant factor, a coefficient, can be moved to the front of the integral. Another way of saying that is when we have a constant multiplied by a function and we differentiate, we know the constant doesn't factor into the derivative. Essentially, we can factor that out just take the derivative of the remaining function and then just multiply it by the derivative at the end. The same thing is true for integration, antidifferentiation. If we have a coefficient multiplied by our function, we can also just take the antiderivative of the function and then multiply the result by that constant. So think of it as essentially factoring out that constant in front of our integral. In other words, the constant does not affect the value we get when we take that integral. Sums and differences. Also the same kind of thing for integration as it is for differentiation. We can differentiate term by term. We can anti-differentiate term by term. Whether we have addition or subtraction does not matter. So if we have an antiderivative of some function plus another function or minus another function, we can split that up and we can take one antiderivative at the time. So this is going to be the same thing as the antiderivative of the first function plus or minus the antiderivative of the second function. So we can look at one function at a time, take individual antiderivatives, which may mean applying different rules to those individual terms. So that's going to allow us to add on some more complicated functions, but simplify them and take them down to those basic rules we looked at a moment ago. So we want to find the following indefinite integrals, in other words, antiderivatives, antidifferentiate, and we're going to assume that x is greater than 0, and we'll see why that matters in just a moment. So what about something like this? Well, we have 3 terms added together, and so the sum difference rule tells us we can just antidifferentiate one at a time. So let's write what that looks like in this case. We can take the antiderivative of our first term with respect to x. We can antidifferentiate our second term with respect to x. And we can antidifferentiate our third term with respect to x. Now notice when I split it up term by term and write 3 different integrals, I'm going to include the dx, the differential, with each of them. Think of the integral symbol and the dx as a sandwich. They always go together. That's the bread on the sandwich. You can't have one without the other, so they always are paired together. Don't ever write an integral without writing d of your variable, whatever your variable of integration is. One without the other is essentially meaningless. Now, what else can we do? Notice for these first 2, we have a function of x multiplied by a constant. So the constant rule says, or the constant coefficient rule says, we can factor out that coefficient and it doesn't affect the antiderivative. So we can pull out that 3, we can pull out the 7, and then technically speaking, we can also pull out the 8 if we want. So let's do that and we'll talk about what happens if that's the case. So now everything is as simple as it can be, and so we can apply, in this case, the power rule. And so we have our coefficient of 3. We're going to integrate x to the 5th with respect to x. So we're going to increase the exponent by 1, so that becomes x to the 6th, and then divide by that exponent or multiply by 1 over that exponent. Now you may be thinking plus c, right? We're just going to do one big plus c for the whole problem at the end. So keep in mind, if we worked it all at one time, we'd have a single constant of integration. Even though we've broken it up into 3 separate integrals, we can also just have one constant of integration at the end. Okay, so next one, 7, and then we're going to antidifferentiate x squared with respect to x. So increase your exponent by 1, divide by that new exponent. So there we go. And then what's happening right here? Well, we factored out the 8 because it was still just a coefficient. What does that leave us with, though? It leaves us with a 1, technically. If we want to think of there as being something there, it leaves us with a 1. So we are essentially just introducing the x. You can think of it as an x to the 0, something like that, where we have the antiderivative of nothing with respect to x. It's really 1 with respect to x. which we could think of as x to the 0. It's essentially the same thing in that case. So that would allow us to apply the power rule. So we increase the exponent by 1, which would take us to x to the first power, just x, and then divide by the new exponent 1, which we don't have to write. And so anytime we just have that constant in there, we can just add on the x. And we actually have a rule for that. It was our first rule up there, the constant rule. We integrate a constant. It just takes us to that constant times x. And so this is essentially our antiderivative plus c. Let's just clean that up a little bit. So 3 times 1/6, well, that's 3 over 6, which is 1/2. So 1/2 x to the 6th. 7 times 1/3, we can just write as 7/3 x to the 3rd power plus 8x plus c. And if we were to differentiate that, we end up with our original function, which confirms that this is the antiderivative. Okay, let's try one more, and then we'll talk about a slightly more complicated situation in more detail what's going on with the c. So we can always begin by taking whatever function we're integrating and simplifying it a little bit. So here we have something that involves division. Well, we don't have a rule yet that's allowed us to differentiate, or excuse me, anti-differentiate something involving division. There is a quotient rule for differentiation. There is not a quotient rule for anti-differentiation. Unfortunately, it's not that simple. But what we do know is that if we have addition or subtraction in the numerator divided by a single factor in the denominator, then we can split it up and just look at one fraction at a time. That's completely legal to do. So we're going to do that in this case to simplify everything so we can go term by term. So 4 over x, we have that, plus 3x over x, plus 2x to the 4th over x. We're differentiating, we're anti-differentiating all of that with respect to x. Now these last two terms could be simplified a little bit further, so let's do that. Now the 4 over x, it is what it is. We just leave it alone. Now 3x over x, the x's are going to cancel, so just plus 3. And then 2x to the 4th over x, 1x reduces, leaving us with 2x cubed. And we're anti-differentiating, integrating with respect to x. So now that we have 3 separate terms instead of one rational expression, we can split this up and we can go term by term. So the antiderivative of 4x with respect to x, integrating with respect to x, plus the integral of 3 with respect to x, plus the integral of 2x cubed with respect to x. Now for each of these we have a coefficient. For the first one it's not as obvious, but that 4 in the numerator, if we were to have a 4 and just multiply by 1 over x, we would end up with 4 in the numerator. So that 4 is really a coefficient for the function 1 over x. So we can factor it out of that integral. Now for the next one, we know there's a rule to deal with this case specifically, so we can factor out the 3 if we want, or we can just leave it as 3 dx and apply that specific rule. And then for the last one, we'll factor out the 2. Okay, so in the first case, the antiderivative of 1 over x, what function would we differentiate to get 1 over x? Well, we would differentiate the natural log function. And notice our directions said we're going to assume that x is greater than 0 in all cases. If x is already assumed to be greater than 0, then when we anti-differentiate and get the natural log function, we don't actually need absolute value because we're assuming that anything plugged into that function is already greater than 0, which means we don't have any issues with signs. Okay, for the next one, the antiderivative of 3. Well, we know if we just have a constant, and that's going to bring the variable back into the picture. And then for the last one, we have our coefficient of 2. We're multiplying by the antiderivative. So using the power rule, increase the exponent by 1, and then divide by that new exponent, plus 1 big C for the whole problem. And so the last thing we want to do is simplify right here. So we have 4 times the natural log of x plus 3x, and then 2 times 1/4, 2 over 4, is the same thing as 1/2. So that is going to be our antiderivative. So this gives us a variety of examples of different ways we can use the rules, we can combine the rules together, and it gives us a lot of different options for taking antiderivatives of a variety of different functions. So now let's talk a little bit more about this issue with C. And so I mentioned so far, just remember, if you differentiate something with a constant, the constant goes away. We don't see a constant here, which means potentially we started with 1 and it differentiated and went to 0. But more than anything, when you take a general antiderivative, you just remember to put the C. So how do we deal with the C? What does that C really mean? So given an antiderivative of our function plus C, the constant of integration, that's C, gives us essentially a class of solutions, a class of antiderivatives. In other words, there are many functions that have the same derivative, but simply differ by a constant. So for instance, suppose we're taking the antiderivative of 2x. We're asking the question, what function did we differentiate to get a derivative of 2x? Well, the 2x would come from taking x squared and differentiating it. But x squared would be one possibility. What about x squared plus 1? Well, if you differentiate x squared plus 1, you get 2x. What about x squared plus 1,000? Well, if you differentiate x squared plus 1,000, you still get 2x. So there's a whole variety of different functions that actually represent an antiderivative to a particular function we're looking at. It's a class of solutions defined by all the different possible values for C. C can take on the value of any constant, and it represents a possible antiderivative for whatever function we're looking at. Well, there's a little bit more we can do with that. So in some cases, in addition to being given the information about how we antidifferentiate, we may also be given an initial condition. What is an initial condition? We're going to think of it as a point, a combination of x and y values that is a solution of the antiderivative. In other words, it's a point that satisfies the function representing the antiderivative. If we're given this extra information about our function, that's going to allow us to solve for a specific value of C. So when we antidifferentiate in general, we have that plus C in order to indicate, again, if we were to reverse the process, differentiate, that differentiates to 0. And so we have a whole class of solutions that solve our antiderivative problem. If we have one extra piece of information about our problem, specifically it's going to be something of the form f of a number is equal to a number. It's going to give us a particular x value, and it's going to give us an associated y value. Having that one extra piece of information is going to give us enough to solve for C, to determine what the actual value of C is that solves the problem we're looking at. So let's try an example where we have an initial condition. So we want to find f of x, find the function, such that the derivative is 2x plus 3, and f of 1 is equal to -2. So this piece of information right here, that's all our initial condition. Essentially, what we're being told is that the point 1, -2 would be on the graph of the function that we're looking for. So how do we know that we're taking an antiderivative? Well, we've been given a derivative, and we've been asked, what's the function that would result in this derivative? In other words, we're reversing differentiation to find our function. The official term for that is what we called antidifferentiation. So our function is defined as the antiderivative of this particular function, 2x plus 3, with respect to x. So this is the derivative. We're asking the question, what's the original function that we would have in order to get this as the derivative? And so we know how to handle this now. And let's just do it all at a time. We don't have to split it up. You can probably do some of this in your head. So 2x, take the antiderivative of 2x. Well, increase your exponent of 1 to an exponent of 2. And then we have our 2 out front. We increase our exponent to 2. And then we're going to divide by that new exponent of 2. So you can probably see what's going to happen right there. Same thing for the 3. We antidifferentiate that, and that's going to go to 3x. And don't forget it, we have our plus c. And so just to simplify that first coefficient, 2 divided by 2 reduces to 1. So we have x squared plus 3x plus c. So this represents a whole class of solutions that we would differentiate to get 2x plus 3. So this is the class of antiderivatives that could differentiate to give us 2x plus 3. Only one of them is going to solve this actual problem though. There's only going to be one actual solution with a particular value of c that would allow us to have this point with this x and y value on the graph of our function. So we know that f of x is now equal to x squared plus 3x plus some unknown constant, c. What does this tell us? Well, this tells us that if we took our function and plugged in a value of 1, in other words, subbed in a 1 everywhere we see an x, so that would be 1 squared plus 3 times 1. Now c is not what we're substituting for, we're substituting just for x. But if we substitute in a 1, the output we get is going to be -2. So essentially we now have an equation no longer in terms of x, but just in terms of c. These two values are constant. This is now a constant, and so we can solve for c based on that. So 1 squared is going to be 1. 3 times 1 is 3, plus c is equal to -2. And so if we move our 1 and our 3 to the other side, we're going to get our value for c. So subtract 1, that takes us to -3. Subtract 3, that takes us to -6. So our value for c that allows us to take this function, a function of this structure, and get a graph that would contain this particular point is going to be the version of this function where c has a value of -6. So our actual function, the actual one we want, the actual individual antiderivative that we want, is going to be x squared plus 3x minus 6. So let's try one more example similar to this one, this idea of taking an antiderivative but actually being able to find the value of that constant of integration. But let's put it into an applied context. So just to review a little bit about this kind of problem, if you think back to when we talked about repeated differentiation, higher order derivatives, we looked at this particular situation. So a physics application, specifically taking a function that represents height or position of an object, taking its derivative, and then taking another derivative. Well, what we determined is that if we were to take a height or position function and differentiate it with respect to time, then the resulting function is defined as the velocity of the object that happens to be moving. So the derivative of a position function is the velocity function. If we were to take the second derivative of our position function, which would mean taking the first derivative of our velocity function, then we end up with a function that represents the acceleration of our object. In other words, how quickly its velocity is changing. Well, if we reverse that process, then we also can use this particular relationship. So in other words, if we have a velocity function, for instance, if we were to anti-differentiate a velocity function with respect to t, well, the velocity function is defined as the derivative of our position function. So we're saying this is a derivative. What function did it come from? Well, if it's defined as the derivative of our position function, then if we anti-differentiate it, we get our position function h of t. And we know, of course, we've got that constant there as well. So that's the relationship we're using here based on the fact that velocity is the derivative of position. Position would be the antiderivative of the velocity function, reversing that procedure. Okay, so let's go through this example. So a rock thrown upward at an initial velocity of 50 feet per second from an initial height of 10 feet has a velocity modeled by the following function. V of t is equal to negative 32t plus 50. So how does this initial velocity factor into this function? Well, initial velocity means at time 0, right when the motion starts. So if you were to plug in t equals 0 right here, that would mean sub in a 0 right here. That would mean your first term goes away and you're just left with 50. Hence the initial velocity of 50 feet per second. So t is in the number of seconds, and then velocity is in feet per second. So the first thing we want to do is determine a distance function h of t, where distance is the height of the rock. In other words, we want to use this relationship. So we've been given velocity, the derivative of our height, our distance function, and we want to reverse, anti-differentiate this function to find the original position function. So h of t, our distance, our position function, is defined as the antiderivative of our velocity function integrated with respect to t. So let's sub in our actual functions. Our actual function is negative 32t plus 50 integrated with respect to t. So we can use our antiderivative rules, go one term at a time. So for our first term, we have an exponent of 1, increase the exponent, so that's going to go to t squared, and then we already have a coefficient. We're going to divide it by our new exponent of 2. And then the same thing for 50. It's just a constant, and we know when we integrate, anti-differentiate a constant, then we have that new variable added in, plus our constant of integration. And so if we reduce negative 32 over 2, that's going to be negative 16 t squared plus 50t plus c. That is going to be our height, our position function. Now, the actual function to model this actual situation is not going to have c. It's going to have an actual value here. Now, we already figured out how the initial velocity factors in. It factors in based on the velocity function, what we were already given. But what about the height function? Well, it turns out we were given an initial condition related to this function as well. We were told that we were starting from an initial height of 10 feet. In other words, the height at time 0, the initial height, has the value 10. Well, we know in general what our height function is, and we know when t is 0, the height function should have an output of 10. So based on that, we can do essentially what we just did in the previous example. We're going to sub in 0 in place of our variable t, and that's going to allow us to solve for c. So h of 0 is equal to negative 16 times 0 squared plus 50 times 0 plus c, and we know that h of 0 is equal to 10. So all of that is equal to 10. Now it looks like it might be relatively complicated, but believe it or not, it's almost instant to solve this. Why is that? Well, look at the two terms that we would otherwise have to move over. These terms just go to 0, which means C is technically already isolated. C is equal to 10. So that means our actual distance function, position function, height function, whatever you want to call it, is going to be this antiderivative where C has a value of 10. So negative 16 t squared plus 50t plus 10. That is going to be our actual function modeling this actual situation. And again, how could we check it? It's always a good idea to check your work. If we were to differentiate this function, take the derivative of the height function, the result should be the velocity function. So let's imagine differentiating this one. We would use the power rule, so bring down the 2, which gives us a negative 32, and decrease the exponent by 1, hence negative 32t. If we differentiate 50t, that differentiates just to 50, hence the 50, and we differentiate 10 and it goes to 0. So that confirms that this would be the function we want that differentiates back to our velocity function. So let's use these two functions to answer a couple of additional questions. So we want to find the height and the velocity of the object after 3 seconds. So we know the initial height, we know the initial velocity. Where is the object and how quickly is it moving after 3 seconds? That's the question. So in other words, we want to find h of 3 and we want to find v of 3. We have a function for h, we have a function for v, we can find both of these values. So h of 3, well, let's flip back over, get our height function, what we just found. So it's going to be this expression, but we're going to sub in a 3 in place of t. So negative 16, 3 squared, plus 50 times 3, plus 10. So negative 16 times 3 squared, plus 50 times 3, plus 10. And we can simplify this in the calculator if we want. Make sure you put parentheses where they are written. So negative 16 times 3 squared plus 50 times 3 plus 10. And that's going to give us 16. Well, 16 what? What is our unit for height? What is our unit for distance? Well, we were told that t is the number of seconds. Well, we were evaluating with respect to 3 seconds. And velocity is in feet per second. Well, if velocity is a rate, feet with respect to seconds, then that means height is just going to be in terms of feet. So that's going to be 16 feet. So 3 seconds after this object has been thrown, it's 16 feet in the air. Well, how fast is it moving at that point in time? That's going to be v of 3. And remember, v was our original function. It was the derivative of our position function. So negative 32t plus 50. So negative 32t, which is 3, plus 50. Okay, so negative 32 times 3, negative 32 times 3, plus 50. And that's going to be negative 46. Negative 46 what? Feet per second. So that is going to be the velocity, which includes both speed and direction, after the object has been 3 seconds released. So this video gave us our general introduction to antiderivatives, the process of integration. Over the next few videos, we're going to add some additional rules for finding antiderivatives, how we can break down antiderivatives, look at them sort of in components. We're also going to talk about what an antiderivative really means, what the context is. We know a derivative has a very specific context. It means something very specific from a geometric standpoint. Well, as it turns out, an antiderivative does as well, and that's going to be the next topic that we're going to explore.